Hi everyone, this is the third video in the series, How to Do an Experiment. The first two videos were Statistical Uncertainty and the Shape of Uncertainty. From those videos, we know to use repeated measurements to reduce statistical uncertainty and to allow use of standard error, which is a measure of statistical uncertainty that can be reduced simply by increasing the number of trials. We also know the shape of statistical uncertainty is Gaussian due to the central limit theorem. When you perform an experiment, you're usually trying to accomplish one or both of two objectives. First, you may be trying to obtain the best estimate for a physical property. For example, you may be trying to obtain the best estimate of little g, the acceleration due to gravity. Obtaining the best estimate of a physical property is called parameter estimation. Second, you may be trying to test a model. For example, you may be attempting to test the equation for the distance an object falls without air resistance, y equals 1/2 gt squared. Not surprisingly, this is called model testing. Parameter estimation and model testing are unfortunately often treated separately, using different methods, despite their interconnections. To understand why this is a problem, let's first clear up what a model is. Y equals AX isn't a model. Y equals AX is a family of one-parameter linear models where X and Y are variables and A is a parameter, a slope, that can take on various model values. X is the independent variable we control. Y is the dependent variable that changes in response to changes in the independent variable. A is called a parameter because it's an adjustable system property. The best value for parameter A in this family of models gives us a specific model. For example, y equals 4.9x is a specific testable model. Because models require specific best parameter values, we can't test a model until we've completed parameter estimation. But unless we test a model, we have no way of knowing if best fit parameters are a good fit to the model. A best fit doesn't mean a good fit. A best fit to the data might still be a bad fit to the model. Fortunately, a consistent methodology exists to perform both parameter estimation and model testing. This method, chi-squared parameter estimation and model testing, is introduced in this video. To accomplish both parameter estimation and model testing, we need reasonable estimates of measurement uncertainties. If we don't know the uncertainties in our data, we can't be sure our best parameter estimates are meaningful. And if we don't know measurement uncertainties, we can't possibly test a model since almost any model will fit data with large uncertainties. Hence, common to both parameter estimation and model testing is the need to have reasonable estimates of measurement uncertainties. Let's look at parameter estimation and model testing applied to a familiar experiment, estimating the period of a pendulum. This is a plot of actual data obtained by students in Harvard's 15A and 16 introductory physics lab courses I taught for 8 years. Some things to note. First, the line shown isn't a best fit line, it's a model line. You see, the model for a simple pendulum that is point mass and small angle can be recast in a linear form as shown on the right. And we have the luxury of knowing the value of parameter A since little g and pi are constants. Second, the data points represent mean values of many trials. So how good does the fit of the data to the model line look? Well, it looks pretty good until you zoom in. The error bars represent one standard error of measurement uncertainty, and we see that the data points are several to many standard errors from the model line. Hence, there's a huge discrepancy between data and model, a gap big enough to drive a truck through. Two takeaways are: first, never rely on eyeballing data in a line to determine a fit. Two, the necessity for error bars reflecting measurement uncertainties. And that requires that the data points are mean values from repeated measurements. Now that we looked at the problem of model testing, consider the problem of parameter estimation via curve fitting. In ordinary least squares, we sum squares of deviations between data and model and find parameter values that minimize the sum of the squares, that is, the least squares. This method dates back to Legendre and Gauss in the early 1800s. The special case involving a linear model later was called linear regression. Ordinary least squares is the method built into spreadsheets and hand calculators. But missing from ordinary least squares are measurement uncertainties. Notice that statistical uncertainties don't appear in the least squares equation. Without measurement uncertainties, we can't reliably do parameter estimation and model testing. So how do we incorporate them? Recall our video on the shape of uncertainty and how the central limit theorem ensures that measurement uncertainties are Gaussians. Note the equation for a Gaussian probability distribution. This is rewritten in terms of data and model at the bottom, where we ignore the prefactor 1 divided by sigma times the square root of 2 pi and substitute a proportionality instead of an equality. It's tempting to ask, given the data, how probable is the model? But no one's found a way to determine the probability of a model. However, if we turn the question around, we can answer, given the model, how probable is the data? In other words, paraphrasing JFK's inaugural speech, ask not, given the data, how probable is the model? Ask instead, given the model, how probable is the data? Given that measurement uncertainties are Gaussian, let's draw a Gaussian centered around each data point and then ask, given the model, what is the probability of generating all the data? Now that's a tall order. So what do you do when you have a problem that seems too tough to answer? Well, nowadays one might say, ask ChatGPT, but that's relying on a tool rather than oneself. One way to approach a difficult problem is to ask if there's a similar but simpler problem. And there is. The simpler but similar problem to calculating the probability, given the model, of generating all the data is to calculate the probability, given the model, of generating just one data point. Now, that's a problem we can answer because of the Gaussian probability distribution centered around each data point, where again, each data point represents a mean. Once we have the probability, given the model, of generating one data point, shown at the top of the slide, how do we obtain the probability of generating all the data points? Well, we follow the rules of probability, where to obtain the probability of a sequence of independent events, we just multiply the probability of each event, as in the probability of flipping a coin twice and getting all heads. A half times a half equals a quarter, and the probability of flipping a coin 3 times and getting all heads, 1/2 times a half times a half equals an eighth. Since each term has a common base, we can sum exponents to obtain the equation in the center right. In order to simplify that equation, we can define a new quantity called chi-squared, denoted by the square of the Greek letter chi. Note that in defining chi-squared, we left off the 2 in the denominator. That's intentional, though for reasons that may not be apparent yet. The result is a nice simple proportionality that the probability, given the model, of generating all the data is proportional to e to the negative chi-squared divided by 2. Hence, the model with the highest probability of generating all the data, and therefore provides the best fit parameter values, occurs when chi-squared is minimum. Chi-squared min is a valuable quantity. To see why, let's look at the relationship between values of chi-squared and the probability of generating all the data. For the one-parameter linear model, y equals ax, chi-squared is a quadratic, that is a parabola, while the probability as a function of parameter values is a Gaussian. Note the switch in terminology. Probability as a function of parameters is generally called likelihood, not probability. The minimum value of chi-squared, that is the vertex of the parabola, corresponds to the maximum likelihood, that is the peak of the Gaussian. In this example, the best fit slope is the value along the x-axis at the minimum of the parabola. Not only can we obtain best fit parameter values from this methodology, but we can also obtain the 1 and 2 standard error uncertainties corresponding to 68% and 95% for the best fit parameters. Note that if we go 1 sigma on either side of the Gaussian peak and extend these lines up to the parabola, they intersect the parabola at chi-square min plus 1. 2 sigma on either side of the Gaussian extended to the parabola intersects at chi-square min plus 4. Where these lines intersect the horizontal axis gives the upper and lower bounds for the best fit parameters. So far we've used chi-square min to obtain best fit parameter values. Then we obtained a 1 standard error uncertainty on these best fit parameter values using chi-square min plus 1. But we can do more. We can answer the question whether a best fit is a good fit by establishing a good fit criterion. For a reasonable fit to data, we expect most data points to be within 1 sigma of the best fit line. Why don't we expect all data points to be on the best fit line? Given that we expect statistical uncertainty in our data, wouldn't a perfect fit be an unlikely and suspect occurrence? Using the good fit criteria of a 1 sigma difference between data and model and substituting into chi-squared, we obtain the sum of sigma squared divided by sigma squared, that is 1 summed from 1 to n, giving n. Hence, chi-squared min should be of the order of n, the number of data points, for a good fit. A more precise good fit criterion can be obtained from the standard deviation of chi-squared, which is the square root of 2. Therefore, the good fit range is n plus or minus the square root of 2n. Maybe this is a good time to review what the chi-squared methodology accomplishes for us. First, it provides best fit parameters from chi-squared min. The best fit parameter values obtained using chi-squared minimization provide a better fit than from what you'd get using linear regression on a spreadsheet or calculator because measurement uncertainties are taken into account. Because sigma occurs in the denominator of chi-squared, data points with greater uncertainties contribute less to the summation, as they should, and those with smaller uncertainties contribute more. This solves the outlier problem, where one data point far from the other data points skews the best fit line disproportionately due to squaring. In chi-squared analysis, if the outlier is a data point with high uncertainty, its contribution will be muted, and if it is a data point with low uncertainty, then it should skew the best fit line. Returning to applications of chi-squared, its second use is in determining if the best fit is a good fit. Using the good fit criterion, the chi-square min should be approximately n, and a more precise good fit range, n plus or minus the square root of 2n, was previously described. The third application of chi-squared is in obtaining uncertainties on best fit parameters, that is, using chi-squared min plus 1. And just like those late night TV commercials that go on to say, but wait, there's more, that can be said for chi-squared analysis as we turn to even more applications. A fourth application is that we now have a metric, chi-squared min, to gauge improvements in experiment or model. If improvements are headed in the right direction, chi-square min will approach n. Finally, a fifth application is an additional model testing method, applicable in some cases. If we have the luxury of knowing reference or true values for parameters, then we can check if best fit parameter values lie outside 95% confidence regions from the reference parameter values. If so, we should reject the model. Let's see how all this plays out in a physics lab experiment. Here are actual results from an MIT 801 mechanics experiment on circular motion, used for many years, to which I added chi-squared analysis. The experiment consists of a ball attached to a spring attached to a rotating shaft. The speed of rotation is controllable, and larger angular speeds result in larger orbital radii. The model can be recast as a two-parameter linear model, as in the upper right. The 5-point data plot with error bars, because every data point is a mean value, and results are shown on the left. We read that chi-square min is 11.79, but the good fit range extends only up to 8.16. Therefore, we are narrowly forced to reject the model. Now, chi-squared is such a sensitive model testing method that it's not surprising to often reject a model, especially on a first attempt. Improvements in the experiment or model can be tried, and the hope is that chi-square min will approach n and fall within the good fit range. In this experiment, large values of angular speed cause the ball to wobble, resulting in large measurement uncertainties at high angular speeds. Constraining the maximum angular speed might improve the fit in a second attempt. A nice feature of chi-squared analysis is that it leads experimenters to revisit their experimental design or revisit the model. This iterative refinement of experiments and models is the scientific method in operation. Since the model has two parameters, chi-squared is no longer a parabola, it's a paraboloid centered over the best fit parameter values A and B. 68% and 95% contour lines are shown in the contour plot on the right. The contour plot tilt isn't surprising, as it indicates that parameters A and B are correlated. We see from the model in the upper right that both A and B include spring constant K, so both parameters are in fact correlated. Links to Python scripts that run in Google Colab and can be modified to do chi-square analysis in your experiments will be posted in the video description. To make the code short and understandable, two simplifications are used. First, all uncertainties are assumed to be in the y variables, not the x variables. This is a reasonable assumption in physics experiments where we can usually precisely vary the independent variable, for example, adding known masses or varying an angle. Second, chi-square minimization is accomplished in closed form, that is, the minimum of a parabola or paraboloid. This avoids need for numerical algorithms, but does limit us to models that are either linear or can be recast in linear form. Just a cautionary tale that things can get complicated fast with multiple parameter models is the following. Most of us are familiar with the fact that 68% of the area under a one-dimensional Gaussian occurs within the mean value plus or minus one standard deviation, and 95% of the area corresponds to the mean plus or minus two standard deviations. But in multiple dimensions corresponding to multiple parameters, this association of 68% to 1 sigma and 95% to 2 sigma no longer holds, as was pointed out by Byron Rowe in the book Probability and Statistics in Experimental Physics, where he cautions that confusion about this point has produced errors in experimental articles in print. So when a former colleague and I co-authored the book Chi-squared Data Analysis and Model Testing, published by Oxford University Press in 2019, we were careful to avoid this error and had this decision to make in our 2D parameter contour plots. We could show the 1 and 2 sigma contours, which would no longer correspond to 68 and 95%, or we could keep the 68 and 95% interpretations, but no longer use 1 and 2 sigma. Sigma values are important only insofar as they lead to useful percentages. So we kept the 68 and 95% interpretations, but that meant adjusting sigma for 2.3 and 6.17 to obtain those probability contours. To help test your understanding of chi-square min and the good fit criterion, error bars, and data plots, try these concept questions by matching letters in the lower right with plot numbers. Pause the video to try. Answers will be provided in the video description. In addition to being an optimal curve fitting method when Gaussian uncertainties are present, chi-squared analysis offers unique pedagogical advantages. It provides a path from introductory physics lab courses to advanced lab courses. Importantly, it improves learning in key ways. Research has shown that critical thinking gains in physics lab experiments require students to be involved in decision-making while experimenting. Chi-squared analysis encourages decision-making because chi-square min provides a metric to gauge improvements when revising experiments and models, so it directly engages students in experimental decision-making. Thank you for watching.